This video is going to cover shear moment diagrams for frames. For this simple frame that we have, we want to draw the shear, the moment, and the axial normal diagrams for the frame. So to start with, we probably want to start by finding the reaction forces. Here at A we have AY, and we've also got AX. And over at the roller at C we also have CY. Since this is 3 equations and 3 unknowns, we're going to just go ahead and try and solve for our reactions first. So we're going to start by summing the moments about A and setting it equal to 0, taking counterclockwise to be positive. And we've got CY. CY is going to be going in the positive direction, so CY and times his distance to A, which is 10 feet. Then we've got no other reactions, but we do have our 4 kip per linear foot distributed load on top. So he's going to be going in the wrong direction. So we have minus 4 times that base of 10 feet times the distance from his centroid, about right there, over. So that's going to be half the base, so half of 10. Then we have that 15 kip load that's up there at B, and he's going to be going the wrong way. So we have our minus our 15 kip load times his distance. We didn't write that in. That's going to be 4 feet and 4 feet, so for a grand total of 8 feet. Then we have our 10 kip load also going in the wrong direction, so minus 10 times a distance of 4 feet. So we have an equation with one unknown. We're going to solve for this. We're going to get that CY is equal to 36 kips. Once we have CY, we can simply solve the forces in the y direction. So sum all the forces in the y direction, set it equal to 0. We have AY going up. We have our 36 kips from CY we just found, and we have a negative 4 kips per linear foot across a distance of 10 feet. So that makes AY equaling 4 kips. And if we sum the forces in the x direction and set it equal to 0, we have 15 kips in the positive direction, 10 kips in the positive direction, and also technically AX with the way that we drew him. So that makes AX going to be 25 kips, but in the other direction. So once we have that, what we really need to do is break it into our different free body diagrams. So we're going to break this beam, and then we need the column in a separate free body diagram, and then lastly we need the corner right at B. So we're going to just off to the side kind of draw those out, and then we're going to fill in our shear moment and axial diagrams. So we've got our beam. This is going to be BC. So we've got CY at the end. CY we said was 36 kips. We have our uniformly distributed load across this member, and that's going to be 4 kips per linear foot, and again 10 feet. We've also got BY. When we break it open, then we've got BX, and we've also got the moment at B. At the corner, this is the corner at B. The corner at B, we're going to exclude this this 15 kip load over here that acts. We're going to say that the 15 kip load is going to act on the column AB here. We're going to not put him in our little free body diagram, because at B we're literally just looking at our internal forces right now. And do remember that they're going to be equal and opposite, so if BY is going up, then on this side BY goes down. If BX is going over to the right, then BX is going to be going over to the left. And if moment at B is going to go clockwise around, then he's going to be going counterclockwise around on the other side. And again, equal and opposite on the other side because everything at B has to equate to 0. So if we sum the forces in the y direction, By again has to be going up, Bx has to go the other direction, and moment at B also has to be going opposite his other partner. Then we have the column. So for our column, we have this is where we're going to put our 15 kip load. And we have our 10 kip load as well. Then we found AY and AX. AY was 4 kips. We said he was going up, and AX we said was 25 kips going to the side. Then of course we've got BY. If BY is going up at B, BY has to be going down. If BX is going over to the right, BX has to be going to the left. And if moment at B is going clockwise around, the moment at B over here has to be going counterclockwise. So a little bit messy of free body diagrams right there, but we do want to just break it up. Now that we have those, we can start solving, and it really doesn't matter where you start. I'm going to choose to start on the beam, though it really doesn't matter where you choose to start. So I'm going to start by summing the moments at B and set it equal to 0. What this is going to give me is the moment at B, since there is a moment at B and he's going the wrong way. Then we have our 36 kips. He's going to be going positive, so plus 36 times a distance of 10 feet. Then we have our 4 kips per linear foot going the wrong way, so minus 4 times his base of 10 times half that base to get over to B from the center. So that's going to give us a moment at B equal to 160 kip feet. If we sum the forces in the y direction and set it equal to 0, we have By going up plus the 36 going up minus the 4 times 10. So therefore By is equal to 4 kips. And if we sum the forces in the x direction and set it equal to 0, we get Bx is equal to 0. And all of that was just for our beam, BC. Technically, if we go and we look and transfer all of our forces through here, so we're just going to transfer those forces. We said By was 4, Bx is 0, so Bx is 0, Bx is 0, Bx is 0, By is 4, By is 4, and then By here is 4. We said MB is 160. 160. If we come over to our column, AB, you'll notice that in the y direction, we have 4 kips going up, and By was 4 kips going down. So summation of the forces in the y direction does equal 0. That's good. We've got our 10 and our 15, and again, Bx was 0, and that equates to 25, so those check out. And technically, we could do the same thing. We could sum the moments about B and find out that the moment at B is, again, 160. However you really wanted to do it, you could. It doesn't matter which one you did. They both get you the exact same answer. So that's kind of convenient. Now all we have to do is just plot our results. So we can start over here at A. So at A for our shear, we're starting at 0 at the pin, and then we've got 25. So we're going to go over 25. Then we're going to be not doing anything. Then we're going to go back 10. We're going to not do anything. Then we're going to hit the very end. We're going to go back 15. So this is our shear diagram. And again, all of this is a 0 degree. Then we've got our moment diagram. And the moment diagram is the area under the curve. So the area under this first curve here is the base times the height, the base being, probably should have wrote that down, 4 feet. 4 feet there. So this is going to be 4 times 25. That's going to take us up to 100. Right, linearly, we're going to go up to 100, starting at 0 at a pin. So we made it up to 100. Then we have 15 times 4. 15 times 4 is 60, so we're going to add that up. So we're going to be going more linearly up to 160, and go figure, that's exactly where we actually left. So there's our moment diagram, ending up there at 160 technically, bringing him back to 0. These are 1 degree slopes. And for our axial, we do have 4 kips pushing on it, so that's going to be compression. So that's just a solid 0 degree slope here of 4 kips for compression. So there's our shears and our moments and our axials for the column. Now for the beam, it doesn't really matter where you start. For axial, there is no axial, it's just a big old 0. For our shears, we said By is 4, so we're going to start at 0. We're going to go up 4, and then we need to go down, 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 down as we go across, and then at the very end we're going to shoot up 36 to get back to 0. So I'm most likely going to screw it up if I don't use a straight edge. So it's just linear, like that. Again, that's all a 1 degree. So 1 degree slope here. And what we need to find actually is this value for x in order to be able to create our moment diagram. Now, technically we really don't have to, but it is kind of important here. One way or the other, we need to find one of those 2 values. So we're going to use similar triangles. So as a big triangle, 4 plus 36 goes all the way up to 40, and that's over 10 feet. And I want to know what the distance x is if I only go up 4. So x is to 4 as 10 feet is to 40. So x is equal to 1 foot. Isn't that wonderful? So if that's 1 foot, that makes this 9 feet, however you want to do it. Remember that at the roller, we're at 0 moment. And if this area is going to be going negative, that means we have to go down to reach our 0, which means this guy's going to be going probably about from here. He's going to be going down, and it's going to be a 2nd degree curve. We're starting off real small, right? Real small over here, finishing real large. So it's supposed to be real large, real small, kind of matching that up. So that's a 2nd degree. And what is the area under that curve? That's 1/2 the base of 9, the height of 36. That's going to take us all the way to 162. And technically this guy, this little dude, he's positive. So we got to go up to hit 162, which means he's going to come back down. So he is 1/2 the base. The base is 1 times the height of 4. So half of 4 is 2. So that would take us back down 2, which puts us at 160, which, hey, look at that. That's where we started, right? Since we have moment at B is equal to 160. So that's our moment diagram, our shear diagram, and our axial diagram. So we are done drawing all the diagrams that we requested. So really, you need to start off finding your reactions first. Then you're going to break it up into your free body diagrams, solve one of them, both of them, all of them, really doesn't matter. But you want to find all of your internal forces, and then it's just simply plotting.